Okay, so thanks everyone for coming, and please help me in welcoming our speaker this week, Dan Hooper. Dan Hooper is coming to us from FermiLab and the University of Chicago, where he is the head of the theoretical astrophysics group. He did his PhD in Wisconsin and a postdoc in Oxford before he settled into Chicagoland. And he's a theoretical astroparticle physicist and astrophysicist as well, who's well known for his many seminal contributions in dark matter phenomenology, cosmic ray physics, neutrino physics, and most recently and famously, his discovery of the galactic center gamma ray excess and its possible origin in dark matter in public Fermi data, which he'll tell us about. So that's going to be exciting. Dan is a good friend and a very singular figure in particle phenomenology. His contributions are delightfully profound and broad. He has been elected a fellow of the American Physical Society for his leadership in the study and search for dark matter. He published several popular science textbooks. He has a cosmology textbook coming out very soon that you can already order on Amazon. He's somehow manages to put out a bi-weekly science podcast, and you can find his, I believe, 80s English punk band called The Spectral Distortions on Spotify, which is a bunch of cosmologists singing about, please don't email Dan about Mond. So with that in mind, we're absolutely thrilled to have Dan with us today. So please join me in giving him a warm welcome.
All right. Thanks so much, David. I should bring you to all of my talks to give the introductions. It's great to be here at the University of Toronto. I was just here visiting CETA a few weeks ago, and it's great to be back. I've had a lot of great conversations with many of you, and we'll have some more later today. Today, I'm going to talk about dark matter, and I'm going to focus on a particular, not model or candidate for dark matter, but a class of candidates, what we call WIMPs, or weakly interacting massive particles. But before I talk about them specifically, let me just give the obligatory slide about just reminding you that we are really sure that dark matter exists. We have a huge and compelling diversity of data, all pointing to the same conclusion that most of the matter in our universe does not consist of atoms, consists of something else, so we call dark matter, that doesn't appreciably radiate, reflect, or absorb light. We see this evidence on a bunch of different scales, all the way from galaxies and even substructure of galaxies, all the way up to the very largest scales that we observe in the CMB, large-scale structure. And they all point to the same conclusion. These observations, however, don't tell us what the dark matter is. They really only tell us three things about the dark matter. First of all, they tell us that the dark matter is pretty long-lived or maybe even stable. After all, the amount of dark matter we measure in the universe today doesn't seem to be any different from the amount of dark matter we measure at early times. So the dark matter isn't decaying or anything like this in a noticeable way. We also know the dark matter is pretty cold. And by cold, I mean that by the time where matter-radiation equality set in around 50,000 years after the Big Bang, the dark matter constituents, particles, whatever, were already non-relativistic. Okay, so that tells us at least some things that dark matter isn't. And then lastly, we know that by virtue of the fact that we haven't seen it in various kinds of experiments that I'll talk about, the dark matter can't interact very much at all with any of the standard model particles. All right, so to motivate WIMPs as a class of dark matter candidates, I think it's important to review how a particle like this, or how a thermal relic would have been produced and how its abundance would have been set in the early universe. So we're going to imagine this particle X. All I'm going to say about it is that it's stable, and at some point in the very early universe, it was in equilibrium. Okay, so it was being produced and destroyed in rates that were faster than the rate at which the universe was expanding, allowing it to reach equilibrium. Then you can calculate how its abundance will evolve using this Boltzmann equation. Okay, so this is number density and its time derivative. This is the Hubble rate. This is its annihilation cross-section. So early on, along this curve, the abundance of these particles can be set very close to the equilibrium abundance. Essentially, these two terms end up approximately canceling, so you get held right along the equilibrium abundance curve. But then eventually you reach a point where these terms become comparable and the dark matter's abundance freezes out. In other words, you stop producing or destroying dark matter particles in appreciable abundances, and the co-moving number density just becomes approximately constant, all right? The abundance you get in the end of this story depends on when this freeze out happens, which in turn is set by the annihilation cross-section of the particles. And the abundance you get today is about the dark matter abundance for an annihilation cross-section in the ballpark of 2 × 10⁻26 cubic centimeters per second. So just to recap, if I have a stable particle that starts at an equilibrium and has an annihilation cross-section of about that size, you will get the right dark matter abundance for that particle. All right, so let's take this one step further. We're going to make 2 pretty reasonable assumptions. One is that these particles were in equilibrium at some point in the early universe. Basically, that's just saying that they don't have vanishingly small interactions. Almost any kind of particle physicists are interested in will satisfy that condition. And then secondly, we're going to assume that the early universe played out like the early, cosmology textbooks say it does. It's all filled with radiation, hot bath, that sort of thing. If you take those 2 assumptions, then we have to be forced to the conclusion that the dark matter has to be heavier than about 1 MeV. If it's lighter than that, it will screw up the successful predictions of Big Bang nucleosynthesis. And also the dark matter has to be lighter than about 100 TeV to avoid being overproduced. So we have 5 orders of magnitude in mass here where we should focus our searches for dark matter, as long as these 2 assumptions are true. Furthermore, for these particles to freeze out of equilibrium to give you the right abundance of dark matter, the measured abundance of dark matter, the interactions of the particle have to be comparable in strength to the electroweak force. The couplings or whatever, however you want to phrase it, of the dark matter have to be comparable to the weak force. This observation is sometimes called the WIMP miracle. I don't know how miraculous it is, but that's what it's sometimes called. So from this perspective, I would argue, and I think a lot of people have argued historically, the dark matter candidates with roughly weak scale masses and roughly weak scale interactions, what I'm calling WIMPs, are a really well-motivated class of candidates for dark matter. So if I was giving this talk 15 years ago, it would be very easy to convince a room of people like you that everything I've said is super reasonable and WIMPs probably do make up the dark matter. Not for sure, but probably do. But then we set out on this ambitious campaign to look for WIMPs, including at the Large Hadron Collider, and they haven't shown up. So the LHC, this is not me throwing shade on the LHC, it has performed beautifully. Functioned as well or better than we could have dreamed, and yet no signs of dark matter or any other BSM physics has shown up, okay? This machine is really good at looking for certain kinds of new physics. It's really sensitive to very strongly interacting particles that can be produced at high rates, like squarks and gluinos. We know that they exist. They have to be a couple of TeV or heavier. It's also really good at looking for particles that give very distinctive signatures, like Z primes that might give you a dijet or dilepton resonance. We know that if those particles exist, they also have to be pretty heavy. In contrast, the constraints that the LHC places on WIMPs are not very strong. WIMPs could be tens of GeV or hundreds of GeV or TeV or whatever, and there's a good chance the LHC won't be able to detect them. So I think from the perspective of the LHC, we can celebrate the successes of the LHC, but we shouldn't conclude that this disfavors WIMPs as a class of particle candidates. Direct searches or underground detectors looking for the elastic scattering of WIMPs have been more impactful, in my opinion, when you think about the nature of dark matter. These experiments have performed spectacularly well. They've increased in sensitivity at a rate that's faster than Moore's law over the last 20 years. So to put that in perspective, think about what your laptop, desktop, or cell phone was able to do in terms of computing power 20 years ago in 2004, and think about how much better your computer is today. Well, over that period of time, dark matter experiments improved more than your computer did. It's a spectacularly successful program, and yet we haven't found any WIMPs in these sorts of experiments. Here's an example of some of the more recent constraints from the Lux Zeppelin program. These are spectacularly small numbers, 10 to the minus 46, 10 to the minus 47 square centimeters. And I think it's fair to say that if you took all of the WIMP models we had that we thought were well motivated 20 years ago and asked, would you expect an experiment like Lux Zeppelin to see these WIMPs? A lot of them, you'd say yes. So the fact that we haven't seen WIMPs yet in an experiment like this really has forced us to contemplate different kinds of candidates and different kinds of models. Okay, so in light of these constraints from direct detection experiments, you might be tempted to say, like some of my colleagues have, that the WIMP paradigm is effectively dead. I strongly reject that conclusion. The constraints from direct detection experiments are stringent, okay? But there still remain many viable model building options to consider thermal relics, things like I would call WIMPs. I'm going to give you a list of some of the ways you could do this if you're a particle physics model builder. And the list will be kind of long, but the common theme that almost all of these ideas are going to have is they involve some sort of mechanism which allows you to have the dark matter annihilate efficiently in the early universe through some sort of diagram like this. But when you turn that diagram on its side and you're scattering with nuclei, this has to be suppressed, okay? So you want to set the right relic abundance while avoiding a big cross-section with nuclei. So the first idea on this list are relying not on annihilations between two dark matter particles in the early universe, but relying instead on co-annihilations between the dark matter and some other state in the early universe. This is an old idea, goes back to this paper by Grease and Seckel in '91. But here's an example in a supersymmetric model where the dark matter candidate, our neutralino, doesn't annihilate with itself, but with a STAU to standard model particles. As long as the mass splitting between these isn't too big, you can get the right relic abundance this way without leading to appreciable scattering rates with nuclei. So this works for a wide variety, not just supersymmetry, a wide variety of scenarios you can write down, so long as this mass splitting is not too big. Another possibility is you could consider dark matter that doesn't annihilate to quarks, but to gauge bosons or Higgs bosons or some combination thereof. After all, there aren't a lot of WZs and Higgses sitting around a nuclei to scatter with. So you take a diagram like this, and to scatter with nuclei, you have to rely on all these complicated loop diagrams. Basically, you have to complete this loop and then connect it to quarks or gluons, okay? That loop suppression pushes down the rates that you expect at direct detection experiments to very small numbers for the Wino and Higgsino-like neutralinos, for example. These numbers are below current constraints. And it's pretty easy in this class of models to have a perfectly viable vanilla WIMP that you won't see in these underground experiments, at least not yet. A third class of possibilities is you can just write down a model where the leading interactions have scattering rates with nuclei that have powers of velocity or momentum exchange built into those rates. A lot of models do this, okay? If you write down something in effective field theory, I don't know, some order 1 fraction of the models will have these sorts of features. And the reason this works so well is that the dark matter in our halo is non-relativistic, has velocities in the order of 10 to the minus 3c. So these sorts of suppressions give you suppressions of the elastic scattering rate at experiments, at the underground experiments, which range from like 1 part in 10 to the million to, or sorry, 1 part in a million to 1 part in a trillion, easily keeping you under these existing constraints. A fourth idea, which is pretty simple, is just to rely on WIMPs that are lighter than a few GeV. These are a bunch of current constraints, and you can see that they're really stringent up here above a few GeV, okay? But down here, well, this is kind of, unexplored territory. So you could easily imagine that the dark matter is a particle with a mass somewhere in the MeV to GeV range, where we just don't have the technology yet to fully explore. That's a perfectly viable possibility. Another totally different class of ideas is we could change our assumptions about the early universe. So I said before, we're relying on this assumption that the universe was radiation dominated, but we don't know that. We don't have any direct information about what the universe was like prior to Big Bang nucleosynthesis. There could have been an era that was dominated by matter early on or some sort of other exotic era. And when you consider these eras, it turns out that the dark matter candidates that can emerge in these sorts of pictures oftentimes have smaller couplings and smaller scattering rates than the ones that we're currently sensitive to. So this gives us a whole model building bonanza to explore. And then last but not least, and then I'll get back to the kind of bigger themes of the talk, you could consider dark matter that's part of a hidden sector. What I have in mind here is a scenario where there's dark matter and some other particles that interact among themselves, but none of which have standard model gauge charges. So they don't have electric charge, they don't have QCD color, they basically interact among themselves. In this sort of picture, the dark matter annihilates not to standard model particles, but to some other hidden sector particles. And then those particles slowly decay through what we call portal couplings to get to reheat the universe and generate standard model particles. Because this coupling can be arbitrarily small or nearly arbitrarily small, the scattering rates in elastic scattering experiments, underground detectors, can be really, really low, easily protecting this class of candidates from all existing constraints. Okay, so I just gave you a list of 6 ways, and I don't want to give you the impression these are the only 6. These are 6 of my favorite ways, okay, to write down dark matter WIMP models, thermal relic models that are completely consistent with all direct and collider constraints that we have today and the nature of dark matter. And you might look at this list and go like, well, if it's that easy to write down dark matter models you can't see, maybe I should be pessimistic about our ability to test the WIMP hypothesis. But I see this list and I reach the opposite conclusion. And the reason I do that is because 4 of the 6 things I put on this list are scenarios that would be invisible, or at least potentially invisible, to underground detectors, but would lead to testable signals from indirect searches, or searches where we're looking for the products of dark matter annihilation. So for example, in the second bullet point here, these particles will still annihilate at the same rate as a standard WIMP, leading to similar levels of gamma ray signals and things as a normal WIMP. The same is true here and here and here. So there's still a lot of opportunity to test the WIMP paradigm, even in this class of models, which are hard to look for in underground experiments. Okay, so let me step back, and the rest of the talk is now going to be on indirect searches for dark matter. And I want to drive home this motivation, which is based on this thermal relic calculation we went through earlier in the talk. Just remember that for a thermal relic to freeze out with the right abundance, it has to have an annihilation cross-section, at least at the time of freeze out, of 2 × 10⁻26 cubic centimeters per second. There are a bunch of model-dependent factors that might make that number be a little higher or a little bit lower in the low velocity, low temperature universe we live in today. But it's fair to say that most WIMP models predict current annihilation rates that are within an order of magnitude or so of that number. So if we can build telescopes, and I have gamma ray and cosmic ray detectors in mind here, so we can build these telescopes that are sensitive to dark matter annihilating with approximately this kind of cross-section at that sort of rate, you can test not just a few WIMP models, but broadly test the WIMP paradigm. You can test a large fraction, an order 1 fraction of the most well-motivated WIMP models. So we already have a lot of constraints from this sort of line of investigation. They mostly rely on gamma rays and cosmic ray antimatter. So here we have constraints on dark matter that annihilates to charged leptons based on the measurements of the cosmic ray positron spectrum. This is a paper I co-authored with Lars Bergström and company a long time ago. And you can see that for these models in which the dark matter annihilates to charged leptons, you can test this up to masses of 1 or 200 GeV. Okay, so dark matter lighter than that, you could rule out in this class of models. In the middle, I have a constraint from a recent paper from the Fermi collaboration, which is based on observations of a series of dwarf galaxies. This is for annihilations to BB bar, but you can see that they're also sensitive up to several tens of GeV for the standard thermal relic cross-section. And then on the right, I have constraints based on measurements of the cosmic ray anti-proton spectrum from AMS. So you can see, again, we're probing a wide range of models up to the weak scale, approximately. And if we could lower these curves by even modest amounts, we can test a lot of very interesting and well-motivated dark matter models. All right, so the brightest signal on the sky, in the gamma ray sky from annihilating dark matter, is predicted to come from the galactic center and the region surrounding, not a point source, but the several tens of degrees around the galactic center. This is a simulation telling us what you should expect to see from dark matter annihilating in these classes of models. And in contrast, this is what the Fermi telescope measures, okay? At least at first glance, they don't look like the same thing. And that's because this is full of complicated backgrounds that swamp the dark matter signal that you might be looking for, okay? This background comes from a bunch of things, including gamma ray point sources and cosmic rays interacting with the interstellar medium. We can try to model it, but I would say there are significant uncertainties in our ability to model this, and that's a real thorn in our side when we try to do dark matter searches using gamma ray telescopes. But despite all of these challenges involving these backgrounds, the signal that would be expected from a kind of weak scale thermal relic was widely expected to be within the reach of this telescope. This is a telescope that should be able to detect this sort of signal, or at least we thought it should be able to detect that sort of signal, if you had a thermal relic in something like this mass range. And lo and behold, when we did the analysis, when he had the data, we found that there is an excess that looks a lot like the signal we had long predicted from annihilating dark matter. This is an excess that peaks at a couple of GeV in energy. And we've tried a wide variety of different background models, and this excess persists against all variations of those models. The signal is extremely bright and very statistically significant. I don't know anybody who works in this field who thinks that the excess isn't there anymore. That is a complete consensus viewpoint. I think this is something that maybe some people would disagree with, but I've tried to state it in what I think should be a non-controversial way. And that statement is that it has been difficult to explain the signal with known astrophysics. Okay, so that leaves open the possibility of unknown astrophysics, and it also leaves open the possibility that it could be explained by known astrophysics in a not so easy way. Those remain possibilities. And like I said, the observed characteristics of the signal are completely consistent with what we had long expected from annihilating dark matter. So let me talk a little bit about those characteristics. So first, the angular distribution of the excess gamma rays, or what we call the morphology of the signal, is roughly spherically symmetric with respect to the galactic center, as you would expect the dark matter signal to be. And the intensity of the emission goes like the distance to the galactic center to the minus 2.4 power. So it's pretty steeply cusped around the inner galaxy. Here's an example shown as a function of angle from the galactic center. And this is the various measurements, and the dotted line is the prediction you get from a simple annihilating dark matter model. We see it out to about 3 kiloparsecs from the inner galaxy. So it's a pretty spatially extended region of the sky. And if you interpret this as a signal of annihilating dark matter, you want a halo profile with an inner slope of about 1.2. For comparison, a standard NFW profile is an inner slope of 1. So this is just slightly steeper than the default NFW prediction. The spectrum, or the energy distribution of these photons, is well fit by particles in this sort of mass range, annihilating to some combination of quarks and gluons. So for example, if I'm annihilating a BB bar, I want a mass of about 50 or so GeV for my particle. It's also worth noting that the shape of the spectrum is uniform across the inner galaxy. Everywhere we can measure it, it has the same shape. And that tells us, for example, this isn't being made by a bunch of cosmic ray electrons, which would cool and have different spectra in different directions. So we can rule out some astrophysical interpretations from that additional information. And then there's the question of the overall intensity or normalization of the signal. So to produce the observed intensity with dark matter, you'd want a cross-section in the range of 1 to 2 times 10 to the minus 26 cubic centimeters per second. Remember that this is very, very close to the value you want for a thermal relic. So this is either just a total coincidence, which it could be, or it's another observation in support of the hypothesis that this signal is arising from a thermal relic that makes up the dark matter of our universe. All right, so at this stage, there's a long history of this excess. It was literally 15 years ago that Lisa Goodenough and I first found this in the publicly available Fermi data. We spent several years simply trying to convince people that the excess was there. Then I'd say around 2014, 2015, that argument shifted from, well, we agree, shifted to an agreement that the excess exists and an argument about where it might come from. And we've had a lot of ideas. People have written a lot of papers trying to explain this with different kinds of astrophysics. But at this point, there are really only 2 hypotheses that really work in light of all the data. One is the one I've been talking about, that it could come from annihilating dark matter particles. And the other is that it could come from a large population of faint but centrally located millisecond pulsars. So pulsars, if you don't know, are rapidly spinning neutron stars who are gradually converting their rotational kinetic energy into emission at, say, radio and gamma ray wavelengths, okay? Young pulsars, or pulsars that are formed as a direct consequence of supernovae, exhibit periods on the order of a second or so, and they slow down and become faint on timescales of millions of years. We have a pretty good idea what the star formation rate is in the inner galaxy, and even if you took every supernova and turned it into a young pulsar, that won't generate nearly enough gamma ray signal to explain the excess. So young pulsars can't be the thing that makes this signal, okay? But there's another kind of pulsar, these alternative ones, millisecond ones, which they evolve along the young pulsar line and then get spun up by a companion, like in this picture, to very, very rapid rotational periods on the order of milliseconds. Because these objects can have much lower magnetic fields by many orders of magnitude compared to young pulsars, they can remain bright much longer than young pulsars. So it's at least plausible that a large number of millisecond pulsars could have been built up, a large population of millisecond pulsars could have built up in the inner galaxy over the course of the Milky Way's history. The literature contains really three different arguments which are made in support of the hypothesis that they could be responsible for the galactic center excess. The first of these is a pretty good argument, namely the observation that the gamma ray spectrum you observe from pulsars, not in the inner galaxy but elsewhere, is qualitatively similar to the spectral shape you measure of the inner galaxy, the excess. So here are two different papers, one, an old one for myself. This is what the dark matter model predicts. This is what the pulsar model predicts. I'm not sure you can tell those two things apart in the data, okay? And here's a more recent study by Ilyas Cholis and Sam McDermott and collaborators finding roughly the same thing. So, you know, it is the case that the excess has a spectrum which looks very similar to that you observe from pulsars, as well as that you'd predict from dark matter. And then there are these two other arguments, which I'm going to try to convince you, I think, objectively now don't hold water, okay? The first is that there's some claims in the literature that the emission from the inner galaxy is clumpy. It has small scale power, maybe indicative of a point source population. And secondly, there are claims in the literature that say the morphology or angular distribution of the excess traces the stellar distribution of the galactic bulge and bar. If either of those were true, it would favor pulsar interpretations over dark matter interpretations of the excess. Okay, so let's talk about the small scale power discussion. This all started back in 2015 when two independent groups, Lee et al., who used a non-Poissonian template fitting technique, and Bartels et al., using spatial wavelet driven techniques, found that the gamma rays from the inner galaxy are more clustered than you would expect from the smooth background, okay? And they attributed this to a population of near threshold, but not quite above threshold point sources. My objection at the time, and what continues to be my objection, is that it's very hard to tell whether these clumps, these clusters of photons, are really arising from unresolved point sources, or whether they are the consequence of inadequately modeling your smooth backgrounds. Okay, so here's a cartoon to make my point. So in this picture, we have this data across some direction of sky. So it's brightest in these peaks and faintest in the troughs. And if you model your backgrounds as a simple smooth curve like this, which you might do if you don't know a lot about your backgrounds, and then you did a subtraction, you would find that the excess, shown as this blue line, looks like it contains a lot of structure. That does not look like a signal from dark matter. It looks like a signal from a bunch of complicated astrophysical sources. On the other hand, I could take the same data, same black line, and I could maybe put in a more sophisticated background model, if you had one, okay, which tells you exactly where the cosmic rays are and exactly where the gas is and so forth. And then you could do a subtraction, and you'd find that that leads to a nice, smooth, dark matter-like signal. My point isn't that we knew which of these was the case when looking at these papers, but that they were both possible. And you couldn't use the data that you had at the time to tell which situation you were in. But then I think this paper settled it once and for all. This is a really great paper by Rebecca Lean and Tracy Slatcher. I will point out that Tracy Slasher was one of the authors on the original non-Poissonian paper. So she's going to kind of flip her opinion here, which is a sign of a good scientist, that when you find new data and new arguments, you change your mind. That's a good lesson to keep in mind. So we're going to show plots like this here to illustrate what they did. So this is from the original 2015 paper, again, Slasher and Slasher, same people. And this shows how much of the emission their template fitting technique is attributing to different components from the inner galaxy. Down here, we have the amount that they're attributing to dark matter. It's consistent with 0. And then this histogram is the amount they're attributing to point sources that make up the excess, and that is inconsistent with 0. So basically, they're saying that in the 2015 paper that all of this is coming from point sources, none of it's coming from dark matter. And the question that Tracy and Rebecca want to ask is, to what extent could inadequate templates being used in these analyses bias this conclusion? So what they did is they reproduced the result, and this looks within, small statistical fluctuations, the same as that last figure I showed you. And this is based on real data. And then what they're going to do to test this scenario is they're going to take the real data and they're going to add to it a simulated dark matter-like signal. Okay, so you take real data and add dark matter. What should happen is that dark matter bit should move to the right, and the point source piece should stay where it is. But that's not what happens. Despite having just added a dark matter-like signal to the data, the dark matter piece stays at 0, while the point source piece moves rightward. So this is clear that clear evidence that the non-Poissonian template fitting technique is clearly misattributing the dark matter-like signal, which you put in by design, to point sources. And that just demonstrates that this analysis is not using an adequate background model to answer the questions it was setting out to answer. This does not mean that the excess could not be coming from point sources. It just means that there isn't any evidence that it is coming from point sources at this time. All right, so that's one of the arguments in favor of pulsars that has been made. The other has to do with the morphology of the signal, and the question is whether the excess looks more like a signal you'd expect from dark matter, like shown in the middle here, or does it look like one of these, which traces some combination of stars in the bulge and galactic bar? Okay. If you found that the excess traced in detail the stellar distribution, you'd be pretty convinced that the stars had something to do, astrophysics had something to do with the excess. On the other hand, if it didn't, if it looked something like this, it would provide support for a dark matter interpretation. There were a series of papers by Gordon Macias and his collaborators and by Bartels and his collaborators where they said that different kinds of bulge templates provided a better fit to the data. Like I said before, if that were confirmed, this would favor pulsar interpretations of the excess. More recent work, however, has not found the same answer. Instead, I think it is now clear that the answer you get in making these comparisons depends critically on various choices you make in your analysis. In particular, it depends a lot on what model you use for the galactic diffuse emission, okay? Kind of like our last lesson. And then also depends on which regions of the sky you include in your fit and which parts of the sky you mask out because you think those parts are difficult to model, okay? So here's an example of one of these analyses. This is by Yiming Zhang and Ilyas Cholis from just a few months ago. The idea here is you have several different morphology models, okay? So here's a dark matter-like morphology. Here's an example of a particular bulge model among several others. And then we have the change in twice the log likelihood. The thing you need to know is the lower you are in this curve, the better the model provides a fit. And each line in here is a different galactic diffuse emission model. Let's focus on the ones that provide the best fit because they're most likely to be a good description of the data. And you can see here that the dark matter model has a higher value of this than the Coleman bulge model. So for this particular choice I'm showing here, the bulge seems to be preferred. But this is for a particular choice of the mask regime or mask scheme. So let's look at another one. So that's the one we just looked at. Here's another one. A different mask. I would say that these are equally reasonable choices for the mask. And now the dark matter model is significantly preferred to the Coleman bulge model. So again, I'm not trying to tell you that this proves that it's dark matter-like. I'm trying to say that this clearly demonstrates the detailed morphology, like the difference between the Kolbe bulge model and the dark matter model, is systematic limited. We don't have a good enough background model or good enough data to tell them apart at this time. It's lost in the systematics. We don't have the power yet to differentiate between dark matter-like models and bulge-like models. All right, so these are the arguments that have existed in the literature in favor of pulsars. I think those two are gone now, okay? Those are completely open questions. We don't have any reason to think those two carry weight or water anymore. There are, however, a couple of arguments that I think are pretty strong against the pulsar hypothesis out there, and I'll go through them in the following several slides. A good question to ask is, why don't we already see more pulsars in the inner galaxy? To date, Fermi's detected only 3 gamma ray sources that could even potentially be pulsars anywhere near the inner few kiloparsecs of the Milky Way. These are their names. Okay, so these are really the only 3 gamma ray sources in Fermi's catalog that could potentially be pulsars attributed to an inner galaxy population. But they could also be part of the disk population. We really can't say one way or the other. Okay, so but at most, there are 3 of these that have been detected. Fortunately, the Fermi collaboration recently put out a new pulsar catalog. Okay, the 3rd one in their 15 years of data. And in that catalog, there are 179 millisecond pulsars from various places in the disk of the Milky Way. My student Ian Holst and I recently did a careful study of that catalog using their sensitivity map and their catalog of sources to try to measure and constrain the luminosity function of these millisecond pulsars. So we used a log normal distribution. For example, our best fit point said that the mean luminosity is like something like 5 or 6 times 10 to the 32 ergs per second, and the width of that log normal distribution was also constrained. And this gives you an idea of what that looks like by eye if you're not used to picturing log normal distributions from the parameters. But you know, this sort of thing peaks in roughly this sort of area, but there's a significant tail in the high and low luminosity ends. We then use this newly determined luminosity function to try to estimate or calculate how many pulsars Fermi should have already detected from the inner galaxy if the galactic center excess is generated by pulsars, okay? So we found that if the gamma excess is produced by pulsars with the same luminosity function, then Fermi should have already detected 20 or more of them in the existing catalog. So here's my contour, which is 20, right? So it goes right through the middle of our best fit contours. But instead, we actually observe 3. So we have an upper limit, which is something like to here or lower left. And yet this is where you want to live according to our analysis. And from this, we conclude that at least one of the following 2 statements has to be true. Either pulsars produce, and this is at a 95% confidence level, but pulsars would produce less than 39% of the excess. Or again, at the 95% confidence level, the millisecond pulsars in the inner galaxy, that population has an average luminosity that's at least 5 times smaller than the same pulsars in the disk of the Milky Way. That latter option, by the way, would require the inner galaxy to contain more than 200,000 millisecond pulsars. I'm not necessarily a pulsar expert, but the pulsar experts I talk to don't seem to think numbers that big are realistic. So this result, in my opinion, puts a lot of pressure, maybe an undue amount of pressure on millisecond pulsar interpretations of the signal. I'm still waiting to see how the community responds to this. After all, this is a new paper. But I think this is a pretty big blow to the community who has been trying to argue that this excess likely comes from pulsars. A second argument that you can level against this interpretation involves low mass X-ray binaries. So millisecond pulsars are formed when they're spun up by a binary companion, like in this picture. And the precursors to MSPs are these objects called low mass X-ray binaries. So naively, you expect places with a lot of millisecond pulsars to also contain a lot of low mass X-ray binaries. There are different stages of evolution. You can't have a large population of one without having a large population of the other. So by measuring the ratio of the gamma ray emission, presumably from MSPs, to the number of bright low mass X-ray binaries that are observed in globular cluster, and when comparing this to the number of bright low mass X-ray binaries in the inner galaxy, we can estimate the number of MSPs that should be in the inner galaxy. So let me put that a different way in math. We measure the gamma ray flux and the number of low mass X-ray binaries in globular clusters. We take that ratio and we set it to the ratio in the inner galaxy, measure the low mass X-ray binary number in the inner galaxy, and try to get out the flux from MSPs in the gamma ray band. When we do that, we find that between 4 and 11% of the gamma ray excess could be attributed to MSPs. Putting that another way, if the entire excess was from millisecond pulsars, the integral telescope should have already detected something like 1,000 low mass X-ray binaries in the inner galaxy, but the catalog actually has only 42 such objects. I see a hand over there. Yeah, let me repeat the question. Basically, the question boils down to, is it reasonable to think that this ratio will equal this ratio, right? I think my naive estimate is yes, okay? But you could imagine stellar evolution scenarios where it would not be true. Now, I don't know if you can imagine ones that would be different by a factor of 20, which is what you need here. That would be rather hard to arrange. But I could easily imagine different populations varying by tens of percents or even a factor of 2 or something. One reason why this is so powerful is one popular scenario for how to get so many MSPs in the inner galaxy is to have them be the tidal debris of globular clusters. If that's the case, then this really should just hold. Okay, so in that scenario, it's a hard prediction. In other scenarios, I think we can be a little bit more open-minded. Good question. All right, so back to this question of what generates the signal. And in my bottom line statement I want you to walk away with is that all the things we measure about the signal are completely consistent with what we had previously predicted from annihilating thermal relics. Okay, so a thermal relic with a mass of about 50 GeV with the cross-section you expect of a thermal relic distributed spatially like numerical simulations tell us dark matter should be distributed should produce a signal that has all the features that have been observed by Fermi. As far as pulsars go, it could be generated by pulsars, but this would require the population of millisecond pulsars in the inner galaxy. It's very, very large, more than 200,000 members. And they would have to have much lower luminosities than we observe anywhere else, and with comparatively few low mass X-ray binaries along with them. So I'm not prepared to say that I think this hypothesis is ruled out, but I am perfectly comfortable saying that it has a lot of tension, a lot of pressure on it. It's a increasingly exotic astrophysical hypothesis. All right, so let's look to the future. I have a few more minutes left. So I want to ask the question of, if the galactic center excess is coming from annihilating dark matter, where else would we expect to see the signal? And could we use these sorts of observations to confirm a dark matter origin of the excess? I think the most exciting place to look are satellite galaxies of the Milky Way, or dwarf galaxies. Already, Fermi has placed a constraint, the solid line here, in this dark matter mass annihilation plane that are pretty interesting from this perspective. So this is based on observations of a bunch of classical dwarfs and a couple of dozen that were discovered by the Dark Energy Survey and other recent surveys as well. You can see that this region, which is favored by the galactic center excess, is starting to be constrained by these dwarf observations. On the other hand, what's really exciting about this is that if you could imagine a way to improve the sensitivity of these searches, this line could go down by a factor of 2 or 3 or something, and you could really test this hypothesis. If you got this line down here, for example, I think I would quickly admit that dark matter can't generate the galactic center excess. There'd be really no way out of that conclusion. On the other hand, if you found an excess that fit this region of parameter space quite well, it would be I think the community would be quick to respond to that and find the dark matter interpretations of the galactic center excess to be very compelling. There have been a number of small excesses observed from dwarf galaxies, from Reticulum 2 to Cana 2, Sculptor, and Willman 1. So here is the test statistic, which is in assuming Gaussian statistics, this is like the square of the significance in sigma, okay, as a function of mass for this particular annihilation channel. And you can see that this sort of band, which is what you'd favor to explain the galactic center excess, has a number of excesses, and they add up to TS of, I don't know, 11 or something, right? At that TS, that corresponds to a total global local significance of about 3 sigma. So I don't know, I don't get too excited about 3 sigma generally, but in this case, we already have a really well-defined target. We don't have any free parameters, and we look at this set of objects with that target in mind, 3 sigma starts to look pretty good. So I think there's a lot to be excited about here. I'm also excited about the fact that this is all about to get a lot better. And it's going to get better because of the Rubin Observatory, which I guess I just checked online a couple of days ago, but they say first light later this year or maybe next year. So Rubin is expected to discover something like 200 new satellite galaxies in the Milky Way, dramatically exceeding the current catalog. Not all of these are going to be useful for gamma ray searches, but some of them will be kind of nearby and otherwise favorable for gamma ray searches. So we're going to be able to take those locations in the sky and look in those directions in the already existing Fermi data. And I think it's super plausible, incredibly plausible, that we'll increase our sensitivity to dark matter annihilation and dwarfs by this factor of 2 or 3, enabling us to finally test this hypothesis, this idea that dark matter annihilating is generating the galactic center excess. So I'm on the edge of my seat to see all this play out. And looking even beyond that, we can consider new, different, better, larger gamma ray telescopes beyond that, what Fermi can do. And what's important here is that a new telescope might not teach us that much about the galactic center, which is systematics dominated, but the dwarf searches are totally statistics dominated. So if you just have a bigger version of Fermi, you can do much, much better in terms of looking for dark matter and dwarf galaxies. As an example, consider the projected sensitivity of this proposed telescope we call APT, or the Advanced Particle Astrophysics Telescope. So here is the region favored by the galactic center. Here is the current constraint from Fermi, and this is the projected constraint from APT. If there isn't a signal there, it could completely rule out galactic center or dark matter interpretations of the galactic center excess. And if it does see a signal, it should not just see a signal from one dwarf, but a whole series of dwarfs. It could detect, half a dozen or more dwarfs at the 5 sigma level. And you would notice that the flux from those individual dwarfs would be proportional to what we call the J factor, which is this line of sight integral over the velocity, over the density profile of the dwarf squared. And if you saw this one-to-one relationship, I think it would be very, very hard to argue that anything other than dark matter generated this signal. This would be an absolute smoking gun. I think even the most reluctant dark matter naysayer would be won over by this sort of evidence. And this would be the thing that I think we could hang our hat on as a clear sign of discovery one day. All right, so I just have a couple of summary slides. I want to thank everyone for their attention and for the invitation to be here. I've really enjoyed my time here. And it's great to have such a clear, enthusiastic audience in full room. It's all great. So in summary, the WIMPs remain extremely well motivated as a class of candidates for dark matter. Direct detection experiments have done remarkably well. In terms of their performance, they've exceeded any reasonable expectations over the last couple of decades. And they have indeed ruled out many of our most well-motivated dark matter models. Indirect searches using gamma rays and cosmic rays are currently testing the range of annihilation cross-sections that we would expect of a thermal relic, at least up to masses on the order of 100 GeV. I would like to extend this to much higher masses, but that's what we have for the moment. And I just want to emphasize here that this isn't some sort of fishing expedition, okay? There are a lot of searches for BSM physics where, well, here's a parameter space that we haven't been able to check. Let's look there. This is testing this thermal relic paradigm. It's this whole idea of anything that was in equilibrium and froze out in the early universe. We are testing that whole paradigm with this class of instruments. Turning to the galactic center, I would say that this excess remains highly compelling, statistically significant, robust, extended, spherical, and not easily explained with any known or proposed astrophysics. There had been a variety of papers in the literature previously arguing that this excess is generated by unresolved point sources, but those papers have not held up to scrutiny. More recent studies have found that the morphology of the signal is consistent with expectations from dark matter. Those arguments, I think, are over. Arguments based on the number of gamma ray bright millisecond pulsars and bright low mass X-ray binaries each disfavor pulsars as the main source of this emission. Gamma ray observations of dwarf galaxies, either in the Rubin era with Fermi or with future large acceptance gamma ray telescopes, will provide critical tests of this hypothesis and provide the opportunity to finally discover once and for all the particle nature of dark matter. Thank you so much.